Hello everybody, I hope you had a good 3-day weekend. R7 continued, R7 got a lot to it. But right now, we're looking at evaluating roots when there's a variable inside of the root. Because it's kind of like, you can't ever take an even root of a negative, and the even root of a negative can't ever be negative. So the input and the output have to be positive. So there's a rules when working with variable that you have to basically put some absolute value around that variable in certain cases. And the rule is this: if n is positive, where n is the root number, and n is the exponent in here, right? If it's positive and even, then you're going to need an absolute value around that variable. But in certain cases, you're going to see that sometimes you can get rid of it because it's redundant. I have a saying that helps this help you remember this rule pretty easily. If n is an odd positive integer, then the nth root of a to the power of n is simply a. So if it's an even root and you pull out a's, it's going to need absolute value. Let's do some example, and then I'll give you my saying that basically says what this says, but I think in a more relatable, easier to understand way. All right, we're going to do some examples. So here, let's do the square root of p to the fourth. Let's do the fourth root of p to the fourth. Let's do 16 in the square root of m to the 8th r to the 6th. Let's do the 6th root of -2 to the 6th power. Let's do 5th root of m to the 5th. And let's do the square root of 2k plus 3 squared. Let's also do one last one. Let's do square root of x squared minus 4x plus 6. Okay. I'm weird. We'll do A, B, C, D, E, F, and G. All right. So this first one, the square root of p to the fourth. So it's square root, which is an even root because the root number would be 2, right? And we're looking for 2 of a kind. So if I was to break this down, I would get p, 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 p. And I'm looking for pairs, and I have one pair of 2's and another pair of 2's. So I'd multiply these together. And we started with an even root, so we would get p squared absolute value. Because if you have an even root, you need an absolute value. But the thing is, since when you square something, it's going to turn out to be positive. In this case, after all, you don't really need the absolute value, okay? Let's take a look at this one. For this one, it's the fourth root, which is even, so we're going to need an absolute value. But if we break it down, it's p, 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 p. So I have one group of 4 p's, so this simplifies to the absolute value of p, okay? Now, this absolute value needs to stay. The reason that this one didn't is because initially we got the absolute value of p squared, but it's kind of redundant because no matter what happens, if you're to square p, it's going to become positive anyway. So I have this say, and hopefully it helps you remember the rule. If you have an even root and you go to an odd exponent, from even, like here, we started with an even root in A, but we had an even exponent when we pulled it out. So we didn't have to have an absolute value. But here, we have an even root, and we're left with p to the first power when we pull it out. First power is odd. So when I say this saying, you kind of need to say it with a southern accent, otherwise it doesn't fully rhyme. But from even to odd, an absolute value is required. Now, the only part you really need the accent for is when you say required. But from even root to odd exponent, absolute value is required. All right, let's take a look at this one. So the square root of 16 is 4. Now, this doesn't really need an absolute value, even though it's even root to odd, because we already know that 4 is a positive number. So we only have to really worry about it for the variables. The square root of m to the 8, how many pairs of m's are we going to have when we multiply all 8 of those m's together? We'll have 4 pairs. So we would have m to the 4th power, right? And how many pairs of r's, if I have r to the 6th, will I get? I will get 3 pairs of r's. So that would be r to the 3rd power. Now, which one of these, I'll give you a hint, only one of them is going to need an absolute value. Which one went from an even root to an odd exponent? From even to odd, absolute value is required. R to the 3rd is an absolute value. Okay, so this one's kind of weird. There is no variable. Remember, there's no variable. You can try plugging in your calculator just to double check to make sure you got the right answer. But let's see here. If I did negative 2 to the 6th power, well, that would be the same thing as 2 to the 6th power. You're going to get the same number if you multiply negative 2 by itself 6 times 6 times 6 times 6. And if you did that, you would get 64. So negative 2 being raised to the 6th power is the same as 2 to the 6th power. Now, I know you might be tempted to say that negative 2 would work here, but no matter what, an even root for an even root can't have an output that's negative. So we're going to disregard any answer that's negative, and the only answer that would work here would be 2. If you simplified this, negative 2 to the 6th power, you would get 64. And if you broke it down, instead of looking at negative 2, you did something equivalent, which would be 2 to the 6th power. Well, then you have 6 2's coming out. But there's no way we could have 6 negative 2's coming out, because that would mean the output of an even root is negative, and that's not possible. You try plugging this in your calculator, but this is kind of a numerical way with numbers of showing you how the variable rule works, okay? And I don't have to say this, because I already know that 2 is positive. I could just say 2. So that even to odd rule really only is necessary with variables, okay? Because variables are unknown. You have to say we'd only look at the positive case. All right. The 5th root of m to the 5th. How many groups of m's, of 5 m's am I get? Only one. So we do have an odd exponent, but in this case, we don't need the absolute value because we didn't start with an even root. Okay. Ooh, this one's neat. So if you were to factor, or if you were to break this down with a factor tree, you would get 2k plus 3 times 2k plus 3. So I have one pair of them. So what I have coming out here is just 2k plus 3. But what is the exponent for this 2k plus 3? It's 1. So if we go from an even root of 2 to whatever coming out being an odd exponent, well, from even to odd, absolute value is required. So this one does need an absolute value. Oh, this one's neat. I like this one. Every time you see, hold on, I copied it down wrong. I do apologize. This is supposed to say +4, not 6. Wouldn't have worked. That's better. Anytime you see something like this, like a trinomial that's quadratic and, you know, and a radical, or when we get onto rational functions, your first thing you're going to want to think about is that can be factored. And if we use magic numbers, what multiplies to 4 and adds to -4? It'd be -2 and 2. So this factors 2. X minus 2 times x minus 2. And since it's square root, we're looking for pairs, and I have one pair of x minus 2. So I could write this as the absolute value. Well, x minus 2 is what would come out. That's what it equal. And because we have an even root, and the exponent of x minus 2 is really 1, because it's x minus 2 to the first power, right? So it's from even root to odd, so this does have an absolute value required. I know it's tricky, and it's a concept that requires some thought, but hopefully we'll practice it, we'll get it. All right, thank you very much.